Hey guys, welcome back. It's another Algebra 2B video. This time we're talking lesson 12.5, Mathematical Induction and Infinite Geometric Series. Now, we're going to focus mostly on the infinite geometric series part. We'll maybe touch on the induction stuff a little wee bit. Now, you remember from lesson 4, geometric series have a common ratio. You're multiplying by a number every time. And series can get very, very big if that number is greater than 1, or they get really small if that number is less than 1. And you can find the sum of some infinite series if there's a specific situation going on. So an infinite geometric series has infinitely many terms. There's two possibilities. If we look here, we have 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. Remember, this is A1, 2, 3, 4, and so on. This one is getting smaller, closer and closer to, let's see, if we add two of them together, we have 3/4, 7/8, 15/16, 32/32, 63/64. We're getting closer and closer to 1, right? And if I were to graph these values, you can see how this curve here starts approaching 1. This one here, a 32nd plus a 16th plus an 8th plus a half plus a 4th plus a half, the next one would be plus 1. This one is just getting bigger and bigger. So as x is going up, the graph just continues to go up. And we're looking at, like I said, the partial sums as we add another term and another term and another term. So we've got two things happening here. In the first one, s sub n, the common ratio is 1/2. We're just multiplying by 1/2 every time. So the partial sum is getting closer and closer to 1, like I said. When your r value, or absolute value of your r value, is less than 1, we say that this series converges. And we actually have what we call a limit. And we can, as we get closer and closer to that limit, that becomes the sum of the series. So you can find a sum of an infinite series as long as the ratio is less than 1. If the ratio is greater than 1, like in the r example there, we say that it diverges, and you can't find the sum because it's just going to continue to get bigger and bigger forever. So first of all, you have to determine, do we converge or diverge? And all you got to do there is find the ratio. If the ratio is greater than or equal to 1, like this one here, 24/20, 1.2, it diverges. So there is no sum for this series. This one here, 1/3/1, the r value is 1/3. That's less than 1, so it converges, and we can find a sum. And if we look at your note sheet, basically that sums up kind of what I just said. An infinite geometric series has infinite terms. When the sum approaches a fixed number, we say it converges. And when the sum does not approach a fixed number, it just keeps getting bigger and bigger and bigger, we say it diverges. What's the difference here? If the r value, the ratio is less than 1, it converges, and it diverges for greater than or equal to 1. So really, all we got to do is figure out what we have here. So let's take a look. To find the ratio here, it's going to be, let's see, -3/2 divided by 1. That's -3/2. So the absolute value of -3/2 is greater than or equal to 1. So this guy diverges. This one here we have, let's see, 64 divided by 256. That is going to be smaller than 1. Let's see, that is 0.25, 1/4. So the absolute value of 1/4 there is positive 1/4. That is less than 1, so this guy converges. So for this one here, we cannot find the sum, but this one here we can. If we look at 3 and 4, this one here, what we got? We got -1/5 divided by 1, so that's -1/5. The absolute value of -1/5 is going to be less than 1, so we converge. Who thinks the next one's going to be diverge? Let's see. 9 divided by 6 is, well, it's 3/2. Just like, number 1, 3/2, absolute value, that is greater than 1. So this guy diverges. So for a problem like number 2 and number 3, I could find the sum of this infinite series. Even though there's an infinite number of numbers, both of these guys are approaching a limit, and the limit is the sum. For 1 and 4, they're just going to keep getting bigger, or they're going to continue to alternate, and we're not going to be able to find a sum. Sorry. All right, so let's go back here and let's see, how can we do it? Well, there's this complicated formula here. If you remember, actually, in 12.4, the sum of a geometric series for any number of terms is a1 times 1 minus r to the n minus 1 minus r. Well, if let's say we got 1/2 as our ratio, work it out, you get 1 minus 1/2 to the n. If you graph the simplified equation on a calculator, you notice the sum levels out and converges to 1, that's the example we saw earlier. So as n approaches infinity, the term 1/2 to the n gets closer and closer to 0. Therefore, the sum of the series is 1. So this leads us to this formula right here. S equals a1 divided by 1 minus r. If you converge, if r is less than 1, then you can find the total sum of the series just by taking the first term and dividing it by 1 minus the ratio. So if we look here at example number 2, part A, 5, 4, 3.2, 2.56, r is 0.8, so it converges. Therefore, I'm going to take my first term, 5 divided by 1 minus 0.8, or 5 minus 0.2, it's 25. And if you were to plug this into your calculator and graph it, you would find that, yes, it's starting to approach 25. This one here, an infinite series, k from 1 to infinity. Look at that, infinity. 2 divided by 3 to the k minus 1. All right, we got to figure out the first term, so plug in 1. 1 minus 1 is 0. Anything to 0 power is 1, so that first term is 2. And then we got 2/3, then we got 2/9. So the ratio here is going to be 2/3 divided by 2, which is 2/6, or 1/3. So the ratio is 1/3. My first term was 2, or 2 over 1. So plug those into the formula. 2 minus, or divided by, I should say, 1 minus 1/3. That's 2 divided by 2/3, and don't be afraid of dividing by a fraction. Remember, just multiply by the reciprocal. So we're just going to multiply by 3/2. You get 3. So let's take a look at the notes here, and yep, the formula we're talking about is right here. Right here. So all you got to do is make sure r is less than or equal to 1. Actually, less than 1, I should say. And if it's less than 1, then you can find the total sum. This one here, the example, 64, 16, 4, 1, and so on. They divide, they get r is 1/4. First term is 64. So we're going to plug those in to the formula. 64 minus, or divided by, 1 minus 1/4. That's 64 divided by 3/4. Keep, change, flip, and you get 256 divided by 3. This one here, kind of again, similar to the example we just looked at in the textbook. This time it's 3 divided by 5 to the k minus 1. So we just got to find at least the first 2 terms. The first term is 3. The second term is 3/5. So r is 3/5 divided by 3, or 1/5. And so, like I said, a1 is 3, r is 1/5. Plug it in, you get that. So let's try it. Let's see. So here we got 81 plus 27 plus 9 plus 1. And remember, I'm going to write it up here. We're going to use S There's no sub n because we're finding the whole thing. It's just 1 minus r. So r is, let's see, 27 divided by 81. Still got to make sure. 27 divided by 81 is 0.3 repeating, which we all know and love as 1/3. And A1 is 81. So basically I'm going to have 81 divided by 1 minus 1/3, which is 81 divided by 2/3, which is really 81 times 3/2, which is 121.5. And you could probably leave it as a decimal, or you could make it 121.5. Same thing. Number 6, we didn't really look at one like this, but your r is right there. R is 0.2. And they did give us the first term. They said first term is 1.2. Plug it in. So we're going to get 1.2 divided by 1 minus 0.2, which is basically 1.2 divided by 0.8. Use a calculator for that. It's pretty simple. You get 1.5. That's it. If we look at number 7 here, r is going to be 1/4 divided by 1, so it's 1/4. A1 is 1, so the sum is going to be 1 divided by 1 minus 1/4, so 1 divided by 3/4. Flip it and multiply, it's going to be 1 times 4/3, which is 4/3. That's it. This one here, r is 0.5. My first term will be 4 times 0.5 to the 1 minus 1, which is 0. So my first term is basically going to be 4, because anything to the 0 power is, I should say, 1. So it's 4. So A1 is going to be 4. So the sum is going to be 4 divided by 1 minus 0.5. So basically 4 divided by 0.5, which is like 4 times 2. It's going to be 8. That's basically it. That is it. The cool thing is you can use this now. You can use this formula to figure out fractions when you have repeating decimals. And I know you guys love to just bust out the calculator, but let me show you here. Write a repeating decimal as a fraction, 0.23 repeating. So if we write this out as a series, it's 0.23 plus 0.0023 plus 0.000023, right? So the ratio here is 1/100th, or 1.01. So we can get 0.23 divided by 1 minus 0.01, or 0.23 divided by 0.99, or 23/99. So when you have two decimals repeating, looks like it's probably 99ths. Probably. So let's try one. Let's try this one here. They said 0.1111, and so on. So rewrite this. It's like 0.1 plus 0.01 plus 0.001. So my ratio is 0.1 divided by 0.1, which is, if you use a calculator, it's 0.1, or 1/10. So the sum here would be 0.1 divided by 1 minus 0.1, or 0.1 divided by 0.9, which becomes 1/9. Pretty cool. So if one decimal is repeating like this, it's probably going to be dividing by 9. If two decimals are, it's probably dividing by 99. And if it's three decimals, it's probably 999. Who knows? But some of your homework is going to be to work that out. Now, we've used series to find the sums of many sets of numbers, such as the first 100 natural numbers. The formulas that you use for such sums can be proved using a type of proof called mathematical induction. I'm not going to spend too much on this because I'm not going to focus on this. You're not going to see this again on a quiz or anything, but I do want to show it to you because it is here and you might have some problems like this in your homework. To prove that a statement's true for all numbers n, first of all, you show it's true for n equals 1, and then we assume it's true for k, and then we try to prove that it's true for k plus 1. So they say the sum of the first n numbers is n times n plus 1 divided by 2. That was something we talked about in lesson 12.2. So let's see if it's true for 1. Plug in 1. 1 times 1 plus 1 divided by 2. Yep, it's true for 1. If n equals 1, the sum is 1. If it's true for k, well, let's see. We'll plug in k. So we'll say k and k plus 1 over 2. Okay. Now let's see if it's true for k plus 1. So we got to add k plus 1 here. Work it out. You need a common denominator, so we're going to use 2. Multiply by 2. Work it out. Factor out a k plus 1. You get k plus 1 plus k plus 2, or times k plus 2, which is really like k plus 1 plus k plus 1. So it works. So that's induction. Easier to figure out is this guy here, example 5, counterexamples. How can you disprove something? The nice thing about mathematical proofs is they have to work all the time. So if you can find one example where it doesn't work, you can disprove something. So if they want you to disprove 2 to the n is greater than or equal to n squared. How do we disprove that? Well, we'll try some numbers. Plug in 0. It works. Plug in 1. Yep, it works. Plug in 4. Okay, it works. So it seems that it's working. But if I try a negative number, oh, no, it doesn't work. So because it's not true for negative 1, it can't be true all the time. So it can't be a mathematical a statement of fact, because if you can prove that it's wrong at least once, then that's all you got to do. All right, that's it. I don't know why they threw this stuff at you in here, because they really don't touch on it again. We won't see it. We won't see it again. So, I don't know. I guess they were running out of stuff to talk about, so they threw this in. Your homework is in Schoology. If you learned something, make sure you smash that like button. And I will see you guys in the next one.